Hi guys, welcome back to part 2 of this introduction to inferential statistics. Now I just want to briefly recap on where we've got to so far. So in research, in order to understand what factors or variables influence the variation in the things that we're interested in, we used statistics. Now there are two main types of statistics: descriptive statistics and inferential statistics. Hopefully, you will all recall that we use descriptive statistics to summarize data. We can calculate measures of central tendency to find the central or most common value in a dataset, and we can calculate measures of dispersion to look at the spread of your data. And all of this can be visualized using graphs. Now, as I've mentioned earlier, you can always refer to the interactive PowerPoint on Moodle to revise these topics further. Now, inferential statistics differ from descriptive statistics, as here we're interested to test hypotheses and make conclusions about our data based on probability. And in the next part of this lecture, we're going to look at how to interpret this probability that we get when using inferential statistics. So when we conduct a statistical test, as part of the output, we will get what we call a p-value. This is the probability value, and by convention, the critical p-value is 0.05. Now what this means is that depending on whether the p-value is higher or lower than this number, this will determine if we can say something is influencing our data. So in other words, the p-value represents the probability that something is or is not significantly influencing our data. Now here, it's a good idea to give a brief background as to where this value of 0.05 comes from. Well, it originally comes from a branch of psychology, where it is supposed that during observations, if something happens less than 5% of the time, these events are said to have occurred by chance. So it is important to know that the p-value is always between 0 and 1, and 0.05 represents 5% of 1. So if we get a p-value of less than 0.05, we can basically say that less than 5% of our data can be explained by chance events, and therefore that over 95% of it can be explained by one or more of the variables that we set out to study. So a p-value of less than 0.05 indicates that something is significantly influencing our data, and we can be over 95% certain of this. But if we get a p-value of greater than 0.05, then we can say that over 5% of our data may be a result of chance events, and we can say that our data are non-significant. Next, we have to put the p-value in relation to the null hypothesis, which, as you remember from part 1, is what statistical tests are actually testing. So as we just said, in statistics, the p-value indicates probability, and by convention, critical p-value is 0.05. So this is the cutoff point where we would either accept or reject the prospect that our data are a product of random chance. So any test giving a p-value greater than 0.05 indicates the probability that a null hypothesis is true. In other words, we can be over 5% sure that our data are a product of random chance events. So we could say that maybe both groups are the same if we're interested in looking at differences, or our data are random. So with this then, the result would be said to be non-significant. On the other hand, Any test giving a p-value of less than 0.05 allows you to reject this null hypothesis. So this indicates that less than 5% of our data are potentially a product of random chance. We're over 95% sure of this. So rejecting the null hypothesis means that the data are significantly different between groups, or data do significantly follow a specific pattern, maybe a correlation. And here we can say the result is significant. Now, to learn more about the p-value and how it relates to the null hypothesis and the alternative hypothesis, you can go to the interactive PowerPoint and follow the pathway to inferential statistics to do this. So, as we have just seen, we can use statistics to investigate variation in a population. But in order for us to make inferences about a population, there are a couple of really important factors that we have to consider. Now, these are that we have independence of samples in our data, and also that we have an adequate sample size. So, in order to understand variation in a population, you need to measure different individuals in that population. You can't just measure the same individuals lots of times. So let's take, for an example, we wanted to look at the effect of testosterone levels on mane colour in lions. If we wanted to make inferences on this in regards to the population as a whole, we wouldn't be able to just take one lion, measure its testosterone levels lots of times, and look at its mane colour lots of times. We would have to look at this in a subsample of individuals. How many individuals we have in this subsample is also quite important. But how many samples do we need in order to make inferences about a population? Well, by convention, in order to perform inferential statistics, you need to have a minimum sample size of 5 independent samples. Okay, so we need to go out and measure 5 individuals. So that about wraps this lecture up. So in summary, in this lecture we have touched on the purpose of statistics. We have looked at the different types of hypotheses and how we can test these using inferential statistics and probability, these being the null and the alternative hypotheses. We have learned about the p-value and how to interpret it. And we have learned about some of the important factors that we need to consider to make valid inferences about populations. Now, as I said earlier, if you do want to learn more about this topic, please refer to the interactive PowerPoint, which you can find on Moodle. But I also do implore you to ask questions about anything regarding this topic in the classroom. Thanks for listening.